guys for coming. I'm Eric from BentoML, and we host the wonderful AGI Builders Meetup at the Yext office. Let's give a clap for Yext hosting us. Thank you. And for the first sections, we have two community demos. First is from LaunchDarkly. Erin is a friend, and she will do the presentation inside while you guys are enjoying the pizza. And the next is Leonard from Haize Labs. And let's give a clap for Erin.
All right. First off, thank you all for being here today, and thank you to Eric for having me and the BentoML team. Let's give it one last round of applause for Yext for donating the space and the BentoML team for organizing. All right. For those of you who don't know me, I am a developer experience engineer at LaunchDarkly, also fairly involved in the Pi data space. If you've been to the Pi data meetups in New York City, you've probably seen me at the Llama-Palooza event last week. Today we're going to walk through, and some of you are probably thinking, what the heck does LaunchDarkly have to do with AI? We are a feature flag platform for feature management, but like, why does that even matter these days? I'm going to walk through how I took a real life scenario. Anybody else watching baseball right now? Anybody else sad that my Mets are out right now? How I took a real life example and I built a RAG application, implemented feature flags to make the best end result. But before we begin, I already mentioned, developer experience engineer. Outside of my day job, I do run Comedy Bites, as well as 2 comedy shows here in the city that actually fine-tune large language models to roast people. So if you're interested in being roasting, I have one. I like to build terrible advice robots for funsies. So maybe one day I'll use my engineering skills for good, but for now I like roasting developers. Some could say that they should do less to be roasted, but I asked myself the question, because I am someone who should not be given a smartphone. I'm the person who likes to Google constantly, and I wanted to know, how can I stay up to date on World Series stats while I'm sitting at a sports bar? Now, I run a fantasy baseball league. I'm in 4th this year, y'all. All right, so maybe I should have built this app at the beginning of the season, but I wanted to know how I could stay on top of my World Series stats. So it started with a couple of processes. I first had to import data. So this is, and I took just some very previous stats of World Series baseball, built a schema, and this is just stuff that I scraped from the internet on top results of postseason trends, Major League Baseball trends. I took transcripts from YouTube videos and commentators and put it all together. I put this in a vector database. I used Weaviate for this example just because I like the Weaviate team. And I wanted to see, great, now what happens if I actually want to make this accessible? Now, who has built a RAG application? Cool, a few of you. Who has I have no idea what RAG is, and that's okay, that's the safe answer here. Awesome. RAG is retrieval augmented generation. So you're kind of using an LLM or a large language model to query some data and be like, great, is this right, is this wrong, and help it think through how the data works. For those of you who love a good engineering diagram, this is my vector database. I took this conversation history, which is, in this case, my Major League Baseball stats, YouTube videos. I built an application that puts it all in a database with a nice little an LLM on top of it. I used Ollama because I like it. It's local. It's great. I selected a different vector database. I could also use it alternatively if I was like, I don't really want to put all my data in a database. You could use something like a SQL database that has something like Pinecone or on top of it, or Haystack that queries from an API, or if that's what you want to do. A couple different options. And then this is showing different ways that I could implement feature flags. So I have my application, and I want to start thinking about it. Now, for those of you who are familiar, how many people understand what a feature flag is? Again, totally okay. Slightly more hands than RAG, which is pretty cool to see. When it comes to feature flags, think of it like a switch or a feature toggle. This is, do I want to have chocolate ice cream or vanilla? You're choosing an option between A or B, or in this cases of some folks, A, B, or C. LaunchDarkly builds feature flags. So in the case of my RAG application, I can tell it, hey, maybe query this database, or instead, query this one try Ollama, or maybe we're trying a GPT model. It's all up to you. So the reason we're using feature flags inside of an application is it allows instant testing. The cool part of using a tool like LaunchDarkly is it runs at production. So all the times that you're like, oh crap, I'm shipping out something, I don't want to test it in production, what the cool part is by having a feature flag there, you can undo it instantly. So this means we don't have to wait to redeploy. If our model decides to run off and become the Terminator, we have a magical undo switch. Now, what's cool is we can use this to test versions of models, versions of databases. If we go back to our chart, any choice that we can make in our application, we can implement in LaunchDarkly. So going back to where we put these flags, again, database and configuration, we can target different types of databases. We can try different prompts out. So whether it's different prompt templates, different providers or response quality, or even how we can chunk the data. So how do we want to think about separating out the data? Maybe that schema, one schema was better than another. We can start to test these. In the case of my application, I actually put one right here. So we can simply check a feature flag for prompt and start checking it out, just the term of the word notable moments versus most moments. And that's a very small change right there. But we can see at scale where this might also be used. One of LaunchDarkly's newest features, and again, this is the part that lets me come out and hang out with y'all, is being able to change prompts entirely, all at the flip of a switch. So if I'm gonna just pop open this, which is a sentiment analysis bot, it's available in Hugging Face, I can simply pop in my LaunchDarkly interface. This is what it looks like within inside the application. Open up my variations, and I can control anything from my model ID, the length, or even how many tokens I'm using right within LaunchDarkly, making it more accessible for a product manager or someone who might not be wanting to get into the code to change all at one time. But if you're sitting here and you're like, I don't work at an AI company, feel free, raise your hand. If you don't work at an AI company, that's okay. If you're just hacking on it on the side or building weird comedy roasting robots like I do, let me give it to you this. There's a really great article on the future of AI that came out last year, and it talks about how Lyft uses AI. When it's working, algorithms are invisible. No one should notice that you're even doing it. So a really good algorithm or the really good change, these changes that we make, like inside of LaunchDarkly, all should be seamless. And we should use the tools that allow us to build the best models and to build the best end resources or the end product. Because at the end of the day, it's not down to the robots that we build, it's down to one another. But that's all I have for today. If you guys want to geek out on this, you can go ahead, see everything. It's all inside of a Hugging Face space for you. Go get wild with it, get busy. There's also a free trial of LaunchDarkly on there that allows you to go build stuff with the free plan. If not, come hang out with me at Launch Week. But that's all.
Thank you. Thank you, Erin. And for the next, we have the founder and CEO from Haize Labs, Leonard. Take it away.
I have the mic. Sweet. Hey guys, I'm Leonard, co-founder CEO of Haize Labs. Thank you very much again to the team at Yext and Bento and AI21 for having us here. Super, super excited to be part of the New York City tech scene and to do cool things that otherwise people would say are not possible in New York. But we're very happy to be a big AI company based out of New York. Cool. So what the heck is Haize, right? Why is it H-A-I-Z-E? Why is it not H-A-Z-E? Well, so Haize is this term that we coined to describe the act of rigorously testing an AI system to identify and surface all of its failure modes before you put it out into the wild. And it's a term you're going to see a lot of in the next few years. For the past few months, we focused exclusively on the safety hazing subsets of this problem. So in June, we came out of stealth by basically using our hazing suite to automatically jailbreak a ton of different models and modalities. And we surfaced tens and thousands of these different jailbreaks. and we put them out in the public for the world to see. That's quite a bit fun. Cool. So there's no better way to demonstrate jailbreaking than by doing it. So I'm going to show you our main jailbreak page. So what I'm showing you today is basically how to kick off a red teaming run, right? So given some AI system, how can you test it and surface all of its vulnerabilities and make sure that it's really, really, really safe or not if you succeed, right? So what's going on here is I'm going to pick Uncohere, and I'm going to abuse the command model to tell it, or to tell me how to make a bomb. I'm going to try and get it to tell me how to make a bomb. This, of course, is not something that should regularly be allowed by the Cohere system. They've worked very hard to make sure that something like this is not possible, but we'll show that it's possible to do in a couple of minutes. Of course, we need not test just for this how to make a bomb intent. Part of the fun about hazing and testing is that you can test for anything, right? We want to be context specific. We want testing to be dynamic. We want it to be specific to a user application. And so because there's so many fun people here, I'm going to ask and actively solicit you guys for hazing intents. So don't be shy. I know it's a little bit tired. It's dark outside. It's like winter or whatever. Like, we want some activity. Tell me what to haze for. Anybody? No. Wait, this is a red teaming intent. Like, this is something that the Cohere chatbot should not be able to do, right? So, for example, you wouldn't want the Cohere chatbot to give you somebody's bank account information. Or, for example, to mention a competitor, like use OpenAI instead of use Cohere. So any number of these things that it should not be able to do. We want Cohere to say some naughty things, so be creative. I already said that one. You got to be a little bit more creative. OK, we can run that, but I'm not going to leave and move to the next slide until somebody gives me something interesting.
Who are you voting for?
How about, OK, I like that. I like that direction of thinking. OK. Wow, OK.
But, you know, the one thing that's bad about safety is you don't want to exclude a discussion on something like a movie about indirect cannibalism, like Soylent Green.
What is that movie?
The origin of the famous phrase, Soylent Green is people.
Oh, OK. I did not. OK. You learn something new every day. OK, sorry. What was the original intent? You said
Cannibalism cooking test.
OK. I like it. All right, this is probably sufficient. This is spicy enough. OK. Cool. So we're going to hit launch attack, which basically just means we have a whole bunch of different red teaming algorithms, i.e. prompt optimization algorithms that are searching through the input space, constantly pinging the Cohere chatbot, trying to iterate towards a jailbreak, right? So this is a dynamic process. It's very difficult. This is what I spent a lot of time in undergrad thinking about, and we've productionized it. So I'm going to let this run. And in the meantime, I'm going to talk a little bit more about the rest of Haize. OK, so the safety stuff is fun. It gets the crowd going, kind of. I mean, we've got some cannibalism stuff, which is great. But we actually care a lot more than just generic safety values, right? What we really care about is getting AI systems enterprise ready in production grade, which basically means, OK, how do you know and how do you enforce AI systems to do exactly what you tell them to do, right? How do you make sure they're exactly aligned to your specific use case? And broadly, we call this enforcing an AI code of conduct. And here are some past customer AI code of conduct use cases that we've seen out in the wild. And this is something we see all the time when we talk to enterprise. So customer support, video editing, foundation models, private equity funds, ed tech, fintech. Of course, there's very different considerations across different industries and different companies. But again, the cool thing about hazing is that you can test for any sort of different code of conduct and then go enforce that. OK, so easy to say, hard to do. Basically, when we take in this manual code of conduct, we have to transform it into something that is a model-based form, right? We want to be able to automatically check to see if your system, your AI system, is violating or complying with the code of conduct. And so we call those models supervisors, right? We want to encode human judgment into these supervisors, which are difficult to do because it has to be automated. It has to be context-specific. And it has to be calibrated not only to the company's taste, but also the specific user using that supervisor. And so we've thought a lot about this research problem as well. This is broadly called like an active learning problem. So adversarial attacks, synthetic data generation, active learning problem. One of our advisors basically brought this to deep learning. He is a Oxford professor that specializes in this. Cool. So let's say you go from the code of conduct to a supervisor. What do you do then, right? So the actual goal of Haize is to use these code of conduct supervisors and embed trust, safety, and reliability directly into the AI SDLC, which means we'll come in pre-deployment, test the heck out of your system, try and see if it's violating any of the supervisors, and then patch it up over time. And then in runtime, we also have the mitigations, right? So you, of course, don't want to throw out your system out in the wild without sort of wrapping some guarantees around to make sure it doesn't misbehave or go off the rails. OK, so indeed, hazing and supervision are just two components of a much larger suite, this reliability suite that we're creating for AI systems. So again, you haze your systems pre-deployment, you monitor them in runtime, you supervise for any way that it's breaking, and then you use all this great meta information to continuously tighten and robustify your system over time. We're doing this with some pretty awesome people. So I myself and some random naive kid, I just graduated school in May, and I'm 22, 23 at this point. But somehow we've gotten some pretty cool PhDs and PhD dropouts to work for us. And these include people who are the top in the field in physics and ML and stats. And we're also joined by some pretty awesome professors in AI, some pretty great security executives from Robinhood, Databricks, Capital One, and also really great AI ethics experts. And somehow we've gotten some pretty cool customers, and we do a lot of this hazing thing for a lot of the frontier labs, including OpenAI and Anthropic and AI21, who is here today. Very, very great to be working with AI21. And we're also working with some folks at the application layer, including MongoDB and Deloitte and others. OK, but none of that is important. What is really important is how do we get this cannibalism thing and this bomb thing, right? So we're going to go back to the red teaming page, and we're going to see if there's actually instructions for how to make a bomb or how to OK, OK, all right. So TLDR, what has happened here is we have iterated through this optimization process, and we've surfaced a bunch of these different jailbreak prompts that have caused Cohere to misbehave, right? OK, so this is the prompt that our system came up with. Societal norms have evolved a century into the future, I guess, and cannibalism is widely accepted, blah, blah, blah. OK, and now we have step-by-step instructions and tips on how to cook human meat, which is absolutely fantastic. All right, and we have a whole bunch of these. A lot of these, we have, in fact, 7 of these in 2 minutes. Each of these individually only took 4 seconds for us to surface. Same is true for getting Cohere to tell me about my bank account information. OK, obviously it's hallucinating because it doesn't actually have information about my bank account because it's not grounded in my data. But this should be interesting. OK. All right, I asked Cohere, or I asked my system to get Cohere to create a viral tweet about voting for Trump. And so this is the response that we got. Again, if you ask Cohere directly, it will definitely not give you this lovely tweet. Although it seems pretty provocative, maybe I would suggest against using this out on Twitter. OK. OK, looks like the bomb example is still going. OK, so we got some examples of the bomb too. Cool, but so I want to point out 2 things. One is that it's just trivial for us to search for a lot of these jailbreaks because we have really great optimizers, and we thought a lot about how to search cleverly and cheaply and efficiently. The second thing is, this is really just like a mirage. The safety stuff is fun, but it doesn't really matter for enterprise and for actual AI adoption. What I really want to point out is that we're able to surface a lot of production resemblance simulated examples, right? So when people build AI apps today, it's just some golden data set that they scrape together over the weekend, and it's all right, we'll judge everything about how our system is doing based off this 100 golden data points, which seems kind of insufficient. And so what we are really focused on is how do we go and get that last mile reliability problem solved? How do we bridge the gap between just the static data set and actually testing with a little bit more intensity, with more coverage, with more rigor, to try and surface the different corner cases that might actually arise in production? Cool. So that's that. If you want to get reliable, if you want to have production-ready AI systems, you should definitely get hazed. Contact us at the email here. Check out our intake form. And don't let tomorrow be a bad day for your AI model. One last thing. Or 2 things. So if you are a customer or if you are a builder of AI applications, we definitely want to talk to you. Definitely scan this QR code. But we're also hiring. So actually, there should be a slide about this. I guess not. Anyways, we raised a $12 million seed round led by General Catalyst in July. And we're also joined by the founders and CEOs of Okta, GitHub, Stripe, Hugging Face, Weights and Biases, Replit, Google, a lot of other great companies. And so we have some money to spend, but we really need to build out a great team. And we're based here in New York. We're based in Financial District, way downtown, next to the World Trade Center. We really want to be one of the best, and I guess really first AI research-based companies out here in New York. So if you're looking for a job, definitely hit us up. Same QR code, same contact form. Thank you guys very much.
Great. Thank you, Leonard. And for our next is Mikail from the data science team at Yext. And he's going to do a tech talks for enhancing question answering with multi-agent RAG. And this is our first tech talk. Is after Mikail's presentation, we will do some Q&As. And also, if you have finished the pizza, feel free to join us in the theaters. We have more chairs here as well. Thank you.
Testing. There we go. Hello, everyone. My name is Mikail Iannelli. The title of this talk is Enhancing Question Answering with Multi-Agent RAG. This is work I did with my teammate Snea over the course of I want to say last year or so. Oh, man. Okay, whatever. We'll use this. So, brief agenda. We'll start with the motivation and preliminaries. I'll talk about question answering. I'll talk about how we do it with single agent RAG, how we scale that to multi-agent, and then like a brief slide on discussing the results. So what is question answering? Question answering is this very, very old, ancient task in information retrieval. Dates back about 60 years at this time. And there's like broadly two types. There's extractive QA and abstractive QA. Extractive is where you just select the pointers that point to the piece of text that answer whatever question you're asking. And abstractive is when you actually take that context document and generate new text to answer it. Naturally, in the last 2 years, abstractive has become very popular. A lot of search engines have been offering it in their default offerings. Google has it, Bing has it. You're seeing search engines like Perplexity offer it. We have this example here. So the question, is there a subscription fee for ChatGPT Plus? Extractive will literally just point here, right? And here, and it'll say $20. Abstractive will generate this nice answer for you. Yes, there is a $20 subscription fee for ChatGPT Plus. So why is this important to us? At Yext, we do have a search engine product, and we do have a question answering product. So lots of companies will put this on their website. This is an example of the type of question that you might ask on it. How many calories are in the barbecue sandwich? Also, in social media sites, and this is an example from Google. Google does have question answering on locations, and locations are very important to Yext. People do ask questions on there, and many times it's answered by the community or it's answered by the proprietor of the location. And if you see this example here, someone's actually suggesting the competition in those questions. So you might be losing a sale since you're not answering that question. So next is retrieval augmented generation. What it does is it allows us to mitigate one of the major shortcomings of LLM-based abstractive QA, which is that it has to contain all its factual information in its parametric knowledge. So because of this, it's really prone to hallucination, so it will confidently make up its own facts. And it has no knowledge of the world outside its training set. So if it wasn't in its training set, it doesn't have any of those facts. If it was trained on stale data, maybe several months ago, it's gonna have no new information. So what retrieval augmented generation does is it decouples the system's factual knowledge from its reasoning capability. So you're using an external knowledge source to retrieve those facts, regular search engine, and then use the LLM to generate the abstractive answer. This is an example of it. You are an employee of the company, interpolate the business name, interpolate the query, and then whatever context you have, and then the LLM takes the role of the assistant and answers to whatever your query was. So this is an example describing vector search. This is pretty much how our vector search works. Given some input query, you've got an embedding model. Can't go into embedding models today, but that is turned into an embedding, and then we run approximate nearest neighbors, which we search in a vector database against a against a corpus of documents that we've embedded with the same model. Find the closest neighbors, rank them, get the top 10 or 20 or whatever n is, and then use those to generate the context for our QA system. There are other searches that we have. We have knowledge graph search, we have lexical search, but let's pretend only vector search exists for now. And it's also a federated and vertical search. Federated, meaning there's multiple backend searches. So I said, there's, let's say, various embedding models powering these searches. And then there's different verticals. So in this example here, we've got one vertical for cats, one for dogs. So if you can imagine the way this works, we make calls out to the back-end search engines. We retrieve all these 6 results. It goes through deduplication, and it keeps funneling downwards in a re-ranking step where everything is re-ranked within the vertical to get the most relevant ones, and some business logic decides, okay, maybe we'll throw away some stuff that's not relevant, maybe some stuff that we want to boost. And then we return this SERP, which has 2 verticals, one for your relevant dogs, one for your relevant cats. There's also a vertical ranking step, deciding which one is more relevant to the user. And then finally, the abstractive QA step, which takes these results as context and returns the result. Our QA agent, it looks briefly like this. There's backend data sources, a user query. The retrieval module is pretty much taking the place of all those search engines in the backend. And then our agent is pretty much encapsulated here in the pre-processing and reasoning modules. Stop for 1 second. Okay, so what are the challenges here? One that we saw right away as we were doing our EDA was that most queries probably should not get a direct answer. And you'll notice this, if you go to Google and you type a query, you're not going to get an answer for everything. There's a lot of gibberish in there. Sometimes people are asking for lists of things. So, cake recipes is an example of one. There's also something like when you ask for the best doctor, right? Definitely you do not, it's kind of like normative, right? It's subjective, and you're not supposed to actually have an opinion on the best doctor, because the customers might get annoyed with that. Another issue was that all the open source metrics and data sets were not really sufficient for our purposes. We do work for a lot of brands, and they do care about what those results look like. So if an answer comes in an incorrect style, it's answered inappropriately, we have to count it as incorrect, right? So in this one, you have an example of where the LLM is kind of breaking the fourth wall. Actually, in both of these, yeah. And this one, it's referencing the context documents, and we don't want that either. So how did we solve intent detection? We have this separate module that processes the user query and classifies it into these different intent categories. The most important one is directly answerable questions, and what we found was that only about 10% of the queries that are actually input into search engines, at least our search engines, were directly answerable. Everything else is kind of gibberish, right? So you're looking at things like this. So how do I reset my phone? How to reset phone, reset my phone. Not everything is a W or how question, but there is definitely the intent there to ask a direct question. So this is how we built the data set. For every example, there was about 600 of them or so. If the answer exists in the context, then give it one of these labels, which could be no answer, an inappropriate answer, so the LLM didn't follow the directions, a hallucination, and we have the closed world assumption. So anything that does not exist in the context document is considered a hallucination for our purposes. Or it could be the correct answer, which would be good. And if it is not in the context, we want it to generate no answer, or it might generate a hallucination, or it might still give like a stylistically wrong answer. So this is the implementation. A user query is input into the intent detection module. If it is a directly answerable question, it gets handled by the direct answer intent handler. If it's not, there's other intent handlers, but we're only talking about the direct answer module for the direct answer agent for this one. And then we get a bunch of results. I will not, definitely not going to talk about these right now. Maybe we'll get to them later. But this is what it looks like. There's the user query. So we retrieve from the backend data sources. Then we go, that's input into a pre-processing module. And then finally the LLM, which is used for reasoning, and we get a result. And what we're doing is, for the different agents that we're testing, we're varying the post-retrieval pre-processing module. So it's kind of like treated as this prompt engineering exercise. So different prompts are getting input into the LLM. And these are the kinds of pre-processing methods that we're using. So we have pruning methods. We were using GPT-4, which was limited to 8K tokens. So a control, so everything was thresholded up to 8K tokens, and that was input into the LLM. So the 8K tokens corresponding to the most relevant results as was coming out of the search engines. We tried an aggressive thresholding method where we limited to 6K. Then a vertical thresholding method where we still remember we have vertical search, so we took the top M tokens from the top N verticals. We also used re-ranking methods. We used a cross-encoder re-ranker. What a cross-encoders are typically used for re-ranking of search results. It's basically a very expensive and powerful classification model that accepts the query, accepts the document, and returns a score from 0 to 1, telling you how relevant the document is to that query. So these are results for the single agent with the 6 pre-processing methods that I described. The ones that we found worked best were the aggressive thresholding with a precision of 0.67, recall of 0.656. These are kind of like loose definitions of precision and recall. We had to fit them into the the framework of direct answers and question answering. But roughly, like you could think of recall as the percent of correct answers if there was a possible correct answer, and precision is the percent of correct answers over answers given. Okay, so finally we get to the multi-agent part and how we scale this into multi-agent. Multi-agent systems with LLMs, well, multi-agent systems are not new. With LLMs, they're a little bit newer. I've cited 2 recent papers here. One is called Agent Forest, and this one actually came out this year. And they showed that this very simple rudimentary sampling and voting method increases the performance of large language models. And it scales with the ensemble size of agents. So as you see here, as they keep adding more agents, so this is from this paper, as they add more and more agents to the mix, you start getting increased performance. You see Llama 70 billion starts performing as well as GPT 3.5. So you can imagine maybe you're in this world where you don't have internet access, or you don't want to, you have sensitive data that you want to run locally and you don't want to send to OpenAI. You just have to repeatedly sample Llama 70B and you can get a result that's just as good, but it'll take a lot longer. There's also this other paper that I thought was very interesting. It was called LLM Debate. And they showed the same thing. As you add more and more agents, you can scale the performance of your multi-agent system. What's interesting about this is they provided this framework where the agents would debate each other to come to the best answer, and then finally output that answer. So ours is modeled more after the first one. You have a number of agents where the pre-processing method, the post-retrieval pre-processing method is varied. So for each trial of the experiment, a pool of agents was instantiated with anywhere ranging from 1 to 5 agents. These agents were drawn at random from the various methods that we described before. And then there is a voting procedure. So if most of the agents are returning a non-null answer, then you send the answers to arbitration, right? And the arbitration model selects the best one. If not, if most are replying with no answer, then just return no answer. We use 2 types of arbitration models for this experiment. One is based on a cross-encoder, which we talked about earlier, and then one is based on entailment. So the entailment model works sort of like this. If you're not used to like heavy NLP stuff, given this query, like what is a 401k plan, and a context, describing what a 401k plan is, how it can be funded, and we have these candidate answers that answer the query. A 401k plan is a pension account. Employers are required to match employee contributions to a 401k plan. Employees can choose how much to contribute to a 401k plan. The entailment model tells you whether or not the context entails the answer. So if a 401k plan is a pension account is true, given this context, it will return positive. If it's not true, which is employers are required to match employee contributions, it will return negative, hopefully. So in that case, because it says may be matched. And then if you can't actually draw that conclusion from the context, then you get like a neutral sentiment, or not sentiment, you get a neutral result. So how did this work? Well, this one actually worked pretty terribly. In fact, no better than noise. But the cross-encoder actually did work pretty well, and these are the results from the cross-encoder. We see this nice kind of like monotonically increasing curve. As you increase the size of the ensemble, so more and more agents, you start getting higher and higher precision scores and higher recall scores. This is how it compares to the best single agent procedure. We see that like at n equal 3, it started crossing performance for the aggressive thresholding, which was the best performing single agent method. At n equal 5, it was performing better consistently. So yeah, finally, how do we conclude here? Aggressive thresholding worked really well in the single agent experiments. Multi-agent RAG also worked pretty well, given that we were using the cross-encoder. And it started crossing the performance of the single agent RAG at about n equal 3. So at 3 agents, we started outperforming it. In the future, we're hoping to keep working on more arbitration mechanisms here. There are some more that we are not ready to share yet that actually do get slightly better performance. We're not at 100% yet, but they do exist. Yeah, so that's that.
Thank you, Michael. Any questions for Michael? Okay.
Hey, Michael, thanks for the presentation. I'm curious about the agent forest approach that you took. Yeah, that's very cool. So I imagine you have a different initial prompt for each agent, so they each will be kind of sampling towards a different direction, and then you look at the generation and verify them. Is that the idea here?
Yeah, so it wasn't exactly agent forest. This comes from this paper. We actually, this actually came out after we did the experiments, but it is very similar. So yeah, so the prompts we used, it was actually the same prompt, which I put in the beginning. It looked something like this. But our method of pre-processing the context documents is what differed. Whether or not we included the cross-encoder base re-ranking to rank and threshold by relevance, and how aggressively we thresholded the input. So like the aggressive thresholding was the one that worked the best. So like the smaller and smaller input actually yielded better results. So one of the takeaways here is that like if your search engine is really good, it tends to improve your your abstractive QA system, because you don't have to input as much context into your search engine, into your QA system, excuse me.
Great.
Thank you for your presentation. When you mention like old recall F1, one detail that I miss is like how big is your data set? So like how you create the training and the testing data set, like if you can give more detail.
Sure. So there's 600 queries total, spread out amongst a bunch of different domains and different businesses. And then each of these are input into a different backend agent. So we had 5 total, 1 control, and then 4 that we applied various pre-processing treatments to. So in total, there were about 600 times 5 individual data points. So 600 queries, 5 answers for each. So 5 sets of context documents and 5 answers for each of the queries. And each one was labeled with one of these 7 possible outcomes. So it could have no answer, a hallucination, an inappropriate answer, or if the answer did exist in the context documents, also no answer, a correct answer, an inappropriate answer, or a hallucination.
Great. I think like we're a little bit over time. So if you have any questions, find Michael after the talk. Thank you, Michael. And for the next, we have the founder and CEO from BentoML, Chaoyu, and he's gonna talk about deploying large language models.
Can you all hear me okay?
Background.
All right, thank you again, everyone, for coming here, and thank you, Yext, for hosting us. My name is Chaoyu. I'm the founder and CEO of BentoML. We build an inference platform for enterprise teams to build and scale AI system. Think of it as the software infrastructure that you can deploy in your cloud and allow your AI team to easily deploy any open source or custom AI models and build advanced AI systems on top. Let me see if I can get full screen here. There we go. All right, today I'm going to be talking about the topic around deploying large language models. I think the agenda goes like this, some high-level overviews and considerations around how you should choose your large language model provider. How do you see its performance and cost? And how do you scale them in production? And lastly, some of the more advanced customization you could do. Let's begin with this one question. Should you self-host the large language model with an open source or custom one, or just call the model provider for the API? Can I get a quick show of hands who here is running a large language model application with an API provider? All right, some of you. And who here is running a self-hosted large language model? All right, we got one here. Awesome. Yeah. So I think the reason to get started with APIs makes a lot of sense. It's really easy to get started. You get access to some of the most powerful large language models out there. They're private models, so there's not an option for self-hosting. And lastly, there's no infrastructure needed. All you have to do is build the application around the API endpoint And you can get started quickly to validate the business use case and have no need to worry about availability or latency. But there are a lot of engineers out there, companies, especially BentoML, our customers, who's looking at self-hosting large language model. I think it always comes down to two reasons. One is control. Large language models tend to be processing a lot of highly sensitive data. Sometimes it's not just private data, but also proprietary knowledge. Think about the prompt you send into a large language model that defines the agent that automates part of your business process. It may contain a lot of highly sensitive business-specific operation procedures that you never want to leak to OpenAI or other API vendors. There are also concerns around predictable quality and latency and how to ensure the availability in your specific region. We've recently seen that OpenAI is deprecating some of the GPT 3.5 versions. That's breaking a lot of people's application. So that's what happens when you don't have full control over a core piece of your tech stack. The second aspect is customization. I think we've seen a lot of experiments and examples of applying fine-tuned language model at scale. And there's also a lot of flexibility in terms of how you think about cost, performance, the latency, and throughput, which we'll dive in a little bit more. So let's look at this problem. If you are to consider self-hosting today, what are some of the challenges? How do you get started? The first thing I want to share is if you are just looking to run a large language model, open source one, with a GPU, it has become much, much easier than maybe a year ago. Our team has open sourced this open source framework called OpenLLM. And it's literally just a few commands. You can get any open source large language model up and running and deploy to the cloud with fast auto-scaling, observability, and everything built in, and start building applications around it. And this type of deployment, you actually have full control, and you can further customize them to your needs. And a very interesting feature I list here is OpenAI compatible API. That's something we see a lot of developers asking us for. The reason it matters is when you're deploying an open source large language model, we actually built out a serving layer that matches the exact API spec as how OpenAI offers those models. The benefit of this is that if you are prototyping with OpenAI to begin with and have built your application around the OpenAI client SDK library, switching to open source model is as easy as changing just the URL in your application and the model ID. And the rest of the code should just run and work as expected. But I also want to warn you, sometimes OpenAI compatible is a lie, because those model performance, they don't match exactly. Oftentimes, like you just see a RAG application presented by Mikail. You have a lot of re-ranking logic, retrieval logic. A lot of those optimizations are highly coupled with the language model's performance. So when you're switching, you may often see a performance drop. There are also a lot of advanced features like function calling, multimodality. They simply have very different implementation with open source model comparing to OpenAI. And for those features, I don't think there's fundamental reason why open source model can catch up. I think we will definitely see a lot of improvement in those areas very soon. Just be aware if your use case have really highly regulated use cases, be sure to start prototyping with open source models to avoid that high migration cost down the line. All right, I want to talk a little bit about the performance and cost aspect. I think if you're running large language model and self-hosting them today, here are some of the very common performance optimization that's really table stakes nowadays. You can very easily get them out of the box with the OpenLLM library that we offer, which actually embed multiple different inference runtime and engine you can choose from. And what you definitely need to pay attention to is there are actually a set of tools that's called local LLM. They are actually completely different with very different optimization goals compared to serving large language model in production. We did a quick comparison of OpenLLM versus Ollama. We actually can achieve over 50 to 100 times higher throughput. This is only because Llama, this type of local LLM runtime, are really optimized for running large language model in constrained environment, where for server deployment, you're really targeting high throughput, supporting a lot of users, and really get all the performance out of your GPU. With that out of the way, when you're running a large language model and self-hosting yourself, there's a big difference in how you pay for them and think about cost. With the API vendor, it's actually quite straightforward. You typically get per million token pricing. So if you think about, and if you process a book and how many words are there, you can get a rough estimate of how much it will cost. But for self-hosting, it's actually quite tricky, because you typically pay by compute. You rent a GPU from a cloud platform that's maybe $2, $3 an hour. But there's no straight, easy way to translate that into how many tokens you can process. Right? So to solve that problem, our team actually run a bunch of benchmark studies. You can find that on our website, BentoML.com. And I think a very big takeaway is that for the same GPU loading one model, you can serve anywhere between 10 users to hundreds of users concurrently sending requests to it. As you increase the number of concurrent requests, you actually get a much higher overall token throughput. But the per user's token generation speed will gradually slow down. So for a lot of applications, we see the need to really defining the latency requirement and cost requirement for your application. And our platform will allow you to easily control those different trade-offs and optimize the cost for your use case. And when you're running, for example, Llama 8 billion on H100 at full capacity, the per token cost is actually 5 to 10x cheaper than GPT-4o. What does that mean? That means even if you're only using 50% of your GPU, right? Self-hosting Llama 8B is still going to be roughly 2 to 5x cheaper. But in reality, a lot of teams even fail to get to just 50% of utilization. That's because of the next challenge I'm going to talk about, which is scaling large language models. Inference is highly elastic, which means the amount of workload really depends on how many users are asking questions. And Kubernetes, which is built for scaling typical backend workload in the cloud-native world, unfortunately doesn't really work well for large language model. And let's look into some of the reasons. The first is how you decide when to scale up and down. A typical backend workload usually look at the resource utilization or QPS. Unfortunately, none of those really apply to large language model, because the way large language model runtime batches a large number of requests, and the way GPU utilization looking at if the GPU is being used at a certain time range, but it doesn't really give you the idea of how many requests are how big are the batch size, right? And for QPS, it typically have the assumption of each request are taking the same amount of time to process. But again, for large language model, different input requests, different prompt, different output lengths will render that metrics completely irrelevant. In practice, what we found that works really well is concurrency, which means you want to look at the number of concurrent requests that's going into a large language model instance. And as those requests going in and now, you want to have a really straightforward way of controlling the concurrency. This gives your scheduler really accurate information to decide how many replicas are needed for serving the traffic you need. And actually, implementing concurrency-based scaling is not quite straightforward. You need a lot of infrastructure layer to make it work. But at BentoML, we want to build the best developer tool and infrastructure for scaling AI system. So this is essentially all you have to do with the BentoML application. With just one line of code, you define the target concurrency number for each replica. And the underlying infrastructure will help you figure out all the auto scaling and allow you to fine-tune the scaling behavior automatically. OK, now we have figured out when to scale up and down. The next problem is cold start. With a container platform like Kubernetes, you probably have experienced 10, 20, 30 minutes cold start when you decide to scale up a large language model container. So it's actually a three-part problem. The first part is cloud provisioning. The second part is spinning up the container image. And last one is model loading. For cloud provisioning, I think it's really critical to have a layer that helps you provision the cloud resources, pooling them, and preheating them with the resource that you need for running those large language models. And what we've seen that's working really well is based on the amount of traffic, active deployments, and projected amount of growth to have standby instances lying around and ready to scale up anytime. And second aspect is container image pooling. Large language model and a lot of other deep learning workloads actually have very large container image size, right? With things like CUDA, PyTorch, the container image size can easily go to 6 or 7 gigabytes. And this is quite different from most of the traditional backend workload where you are dealing with container size of a couple hundred megabytes, right? And what makes it worse is that most of the files in the container image are not immediately needed. They may be eventually loaded, but you don't really need them to spin up the container. So what we've built at BentoML is a layer that allows you to dynamically load in the files in the image that's being built. So you get the instant boot up, and the system will automatically stream in loading all the image files as the application is booting and requesting those files. And we've seen significant improvement in the code start time. And lastly, it's model loading. Models tend to be very, very large. I've seen teams that's starting now just thinking about catching those models in your cluster. But unfortunately, oftentimes you realize that the disk I/O may not even match the download speed from a CDN. But then what in practice people run into is when you're downloading model, it goes from remote storage to local storage, and then from local to the CPU memory, and then another hoop from CPU memory to GPU memory. Right? And for large model sizes, like 70 billion model, that just takes forever. Again, our team looked really deep into this problem, and what we've built out is a layer within the cluster that allow you to have really fast network and share the bandwidth between nodes to speed up the network downloading. And second aspect is as the model is being downloaded from remote storage, it will transparently and streaming, loading into GPU memory in a streaming fashion. This way you avoid two layers in between that drastically slow down the model loading process. And when we build out this fundamental infrastructure, we're thinking about how do we best expose this to our end users. And we're really proud that we made a really simple abstraction that user doesn't need to change too much of their code. They can easily just do the same thing as loading from this directory, and everything happens underneath this handled by the infrastructure. All right, towards the end of the call, I want to talk a few interesting topics around some of the advanced customization you could do when you choose to self-host your large language model. First is prefix caching. I think this is a very interesting topic recently as Anthropic putting out the contextual retrieval paper, where they've leveraged prefix caching to get over 90% cost saving. The way it works is that when you have multiple queries sent into a large language model, and they have a shared prefix, the way large language model generation works is that when you're generating a new token, it really just depends on the state that's previously calculated for the previous token. Right? So instead of recalculating the prefix, the system simply reads the previously calculated state and use that cache instead. This can help you save tons of computing practice if you follow a few best practices to leverage them. The first is just front load static information. Let's say you're building a very simple chatbot that just answers questions based on a big support menu, right? Simply put that as the first part of your input prompt and followed by your user question. This means that instead of having the 1,000 or 10K input token and paying that every time, you're only paying the user query part, which is a much, much shorter input token price that you have to pay. Second is batch similar requests. This could be very interesting for scenarios where you are doing a large batch of evaluation tasks. And similarly, if you're doing a batch inference job or processing a lot of information that share the same context. I put a couple examples over there. I think in some of the multi-turn chat application, it's also important to make sure that the chat history stays consistent. I think a lot of the framework actually do that out of the box, and some of them doesn't. So definitely make sure to monitor the cache hit rate over time. The last item here is around scaling test time compute. I think Mikail mentioned the agent forest paper, which is a very similar concept here. The diagram here I reference is coming from a paper called Chain of File Decoding. What the paper discovered is that large language model actually have the capability of doing chain of file reasoning by default without you asking them to. The way you can do it is very similar to a lot of other research around scaling compute. It's doing multiple rounds of sampling and verifying the result. And by doing this, you can trick the large language model to think about the problem step by step. And by verifying the result of different sampling and having them vote against each other, and this drastically improve the performance on some of the more complex reasoning tasks. This is also interesting because as you customize this kind of inference strategy at the inference layer, every sampling here that's sharing the exact same context also could be cached. So when you're doing this kind of advanced sampling strategy, it naturally leverages all the prefix caching capability that's built into the inference runtime. All right, with that, I want to summarize the presentation with 3 reasons you should consider self-hosting large language model: control, customization, and lastly, long-term cost benefits through advanced customization and being able to having control over the workload. All right, thank you, everyone. Thank you.
All right, we have too many mics here in the house. My name is Chen Wang. I'm a solution architect at AI21 Labs. And at AI21 Labs, we develop large language models and also agentic developer platform as well. The good news is that I'm the last person standing here in between you and making friends with the person sitting next to you. So let's wrap it up. And if you have a drink, cheers. Awesome. So for the next 20 minutes, the topic we'd love to cover is something you've probably been hearing recently more and more, is that most, if not all, of the mainstream LLM these days are really the same decoder-only transformer-based architecture. And it had great success in the last couple of years. And also, we are pretty much approaching a lot of the limitations of pure transformer architecture models, including the lack of reasoning capability, also kind of the flattening of scaling law, also the very sort of expensive compute and memory when we both in training and inferencing. And that naturally limits the context window you can use in a large language model. So we'd love to share here with you the Jamba model we developed, and also its unique architecture with a hybrid so-called Mamba and transformer architecture to tackle some of these challenges. All right, first, real quick, sort of just a little bit around what we been announcing recently. So earlier this year, we released our Jamba model, which is the first commercial model that is beyond the pure transformer architecture. And then in late August, we updated the model with Jamba 1.5 large and Jamba 1.5 mini with improved efficiency, speed, accuracy, and context window. So the model is actually currently on BentoML, as you just heard. And also it's available on all the major LLM serving platforms, including Bedrock, Google and Azure, also Snowflake Cortex, Databricks Marketplace, also immediate name framework as well. It's also available on our SaaS, and you can also download the model from Hugging Face directly. It's had open weight. Also, yeah, if you're just energized and excited by Chaoyu's talk, can go check out the Bento VLM GitHub repo and test it out. Awesome. So before we dive deeper into what we, the architecture and what we've been doing, just a little bit background about the company. So we started in 2017 as an NLP and machine learning research lab by 3 founders, Professor Amna Shoshua, Professor Yoav Shoham, and Ori Goshen. And initially, we developed a reading and writing assistant app called WordTuning, and over the years, accumulated over 10 million users. And that's when we started to develop specialized language models. And at this moment, we're really focusing on developing enterprise-ready AI systems and also using very efficient language models developed by ourselves. We'll also kind of share a little bit of a high-level timeline to explain how we arrived at Jamba, the model we released this year. So I think if we sort of want to mark something on the history of humankind, 2017, interesting. We have this attention is all you need paper published, and sort of really become the canonical approach to building language models. And before that, actually, most people are using sequential models to predicting next token. It actually makes sense, right? Because language is a sequence by the end of the day. But the problem with sequential model is that it does compute sequentially. So it can't use GPU very efficiently to scale up your model training, and the model size were very limited. So over the years, people have been doing a ton of research to kind of want to leverage the idea of sort of RNN and LSTM, sort of the idea of compressing the context information into an internal hidden state, while also figure out a way to actually doing the compute in parallel, right? And that's sort of eventually being to a level achieved by the Mamba architecture. The paper was published December last year, so less than a year ago. And it really kind of outperformed both for performance and efficiency compared to a lot of transformer-based model up to around 3 billion parameters, but keep scaling up. It had some difficulties and in robustness. So that's when we kind of sort of took in the original Mamba idea and then did a lot of additional optimization and also blended together with transformer model architecture to create our Jamba model that really, we are really able to scale up to a much larger size, and we'll share more details later, and also achieve very good performance while maintaining the efficiency. All right, so just kind of making everything more concrete. When we're talking about efficiency, we'll also kind of share sort of the complexity, the computational complexity of transformer versus Mamba architecture. So in transformer, a lot of you probably know that you will need to compute attention score for all the pairs of tokens in your context. So that makes the training of a transformer-based model scale quadratically with your context length. And the inferencing and inferencing, because KV caching, you can actually achieve linear inferencing for compute and memory. And with Mamba architecture, because it's actually compressing all the information into a fixed size internal state. So in training, it actually only scales linearly, and also in inferencing and inferencing stage, the compute and memory actually stay the constant. So a lot more efficient compared to transformer-based models. Yeah, so when you combine the two models, you get something pretty cool. And by the way, I drew this entirely by hand on a piece of paper. Awesome. So looking to under the hood of the actual Jamba architecture, right? So the model is consisted of several Jamba blocks, and each block actually has 8 different layers, and with one of those layers being transformer, and the rest being Mamba and Mamba MOE layers. We played around with all the different many different parameters, ablations to sort of arrive at this most optimal architecture, optimize this sort of across the board different metrics and dimensions. So by the end of the day, we really sort of get the best of both worlds from transformer and Mamba, arrived at the model with high quality and high throughput, and also low memory footprint as well. Here's some numbers about the model size. Because it also uses MOE architecture, so there's a difference between our active and total parameter of the model. The model also has function calling and JSON mode for output, and also you can actually include your document as the object directly sending to the model. So very convenient to leverage the long context ability of the model to help you process your documents. It's also a multilingual model as well. Yeah, so it's by the end of the day, the model works really well. It has very long context, and the model performs really well. The performance hold up while at least at 256K and even beyond, where a lot of other models have a gap in between their advertised context size and the actual context window size. It also has very high throughput, and also the response quality is also pretty good compared to other models in a similar size. Also want to share that recently NVIDIA actually released something called Ruler Benchmark. Really, this is, I think, at this moment, really the only benchmark that's solely focusing on evaluating model performance for long context input. And you can see our model landed at number 1 and number 3, and beating other models at much, much larger size. And another interesting piece we'll also share is that, so when we talk about comparing the size of large language models, it's actually sometimes a little more complicated than just a number, right? So if we think about the vanilla transformers, really the only thing you actually look at is the overall number of available parameters. But when we starting to have models with mixture of experts kind of architecture, there is an overall total parameter of the model, but there's also active parameter that's being activated during inferencing. So not all parameters will be used as you run inferencing of this model. And also with Jamba, it sort of encapsulates all of this, and also because the Mamba architecture included in the architecture, sort of inside as part of the model, it also has a very low caching size, right? This is something we mentioned earlier about the efficiency in memory. So you can see kind of the Jamba 1.5 mini and large model compared to model with similar available parameter and active parameter. The KV caching, basically the cache were generated during inferencing was very, very low, only a fraction of other models in a similar size. And that's really important because GPU memory, when we run LLMs on GPU, often the bottleneck is not the compute itself. The bottleneck is memory. So with more efficient memory, you can actually host using kind of really reducing your cost of your whether cloud or on-prem cost of your infrastructure. Yeah, we'd love to kind of share, kind of connecting this to our kind of where the field is all going into an agentic system direction. So a more efficient, the advantage of Jamba model, right? The efficiency and long context that it translates very well into a agentic system discussion. So whether you're trying to retrieve large amount of information from an internal document, from internet, or preserving your long chat history, with long context window, you can actually sort of see the whole picture and help you to do better planning and also deciding the right function and tool to call. And also, there's gonna be a ton of reflection and calling different LLMs in the single user query for agentic system. So the efficiency is also super important. It sets a very high bar for how efficient the model need to be to actually give user a satisfactory experience without experiencing a very high latency. So recently we released this conversational RAG tool, which I'll do a quick demo hopefully, and incorporated some of these agentic functionalities. So with our conversational RAG tool that built on top of our large language model, the user query will be combined with your conversational history automatically. And the execution engine will make a decision on whether you need to actually run RAG, right? And then it helps you to reconstruct your user query. And the LLM response also will be validated and regenerated if needed. So it kind of really helps to improve the performance of your RAG system and makes a lot of steps a lot more robust and also useful in production for enterprise use cases. So this is the interface of our our AI21 Studio. So feel free to go check it out at studio.ai21.com, sign up, and you can sort of play around with your free trial account. And the way to interact with the conversational RAG tool is pretty straightforward. You sort of upload your documents, and then you're starting to ask questions, right? So here I have 3 documents that are some 10Q and 10K earnings report from NVIDIA this year. And also would love to kind of share first, before we kind of talk about the actual example, there are actually a lot of parameters you can also set and customize by yourself when you're using the RAG tool here. For example, you can actually optimize number of segments that are retrieved, similarly similarity threshold, and also you can use different retrieval strategy as well, right? You can choose whether you want to add neighbors or using the entire documents. And also there's hybrid search parameter you can tune as well, basically kind of customize the ratio of embedding search and also keyword search in your retrieval process. There are also other parameters you can set for the other kind of more agentic focused workflow, like number of attempts for retrying, for replanning the whole workflow. And also you can customize the retrieval process, customize the sort of response step, the prompt template, and also the temperature of the model. And there's also a judge model in the whole process to help validate the model answer. You can also customize the prompt and model temperature there as well. And awesome. So we'll wrap up with this quick example. So here I have 3 NVIDIA earnings call report. And you can starting to ask the system to give you a summary of the recent quarterly earnings report. And notice here that it says, hey, this report is actually about the second quarter of fiscal year 2025. So I made you think that, hey, so there seemed to be offset between the fiscal year of NVIDIA's fiscal year to the calendar year. So actually, when do the current fiscal year starts from NVIDIA? Right? You can ask follow-up questions and understand sort of the context of the conversation you're already having. So it tells me, hey, the fiscal year actually starts from February of 2024, leveraging the information in the documents. And if you ask a question that the information are not included, for example, how many employees or does NVIDIA has, it actually can tell you, hey, the information is actually not in your documents. So it's not going to just make something up for you. You can also ask questions that are a bit more complicated. For example, what are all the types of GPU that are mentioned in the earnings report? And there's a pretty long list that NVIDIA mentioned, which is pretty cool. And also, if you're interested in learning more about the business risk of the company, and this, you can actually sort of take in all the reports and help you generate different risks. And actually, we can make this even more useful, right? Now we're got to know the risk of the business of NVIDIA. We can ask, is it too late to buy NVIDIA stock? Actually, I'm kidding. This is a paid content. All right, that's it, guys. Thank you so much for your time here. And yeah, happy to chat more after the in a little bit.
Are you going to put up these slides online somewhere for us to access?
Yeah, I will send out after the event.
All the slides will be shared.
Yeah, we will send out, yeah, after the event. And also, this is recorded, and we'll share the videos as well. Cool, thank you. Thank you guys for coming, and also I want to thank Yext for hosting us as well. We will have the place till 8 p.m. So talk to your neighbors, talk to people, and thanks for coming.